The eruption came without warning, from a volcano many believed had gone silent long before recorded history even began. In the barren volcanic plains of northern Ethiopia, Haile Gubbi had rested for roughly 12,000 years. It stood in one of the most geologically unstable regions on Earth. Yet for millennia it gave no visible sign that magma was still moving beneath it. Then, on November 23, 2025, that silence ended. A towering ash plume burst nearly 9 miles into the sky, climbing to around 45,000 feet, or almost 14 kilometers. Within hours the cloud had drifted beyond Ethiopia, crossing the Red Sea and spreading over Yemen, Oman, parts of Saudi Arabia, and eventually as far as India and Pakistan. Aircraft warnings were issued across multiple countries as ash moved through international air routes. What began as a remote volcanic eruption in the Afar depression quickly became a regional atmospheric hazard. But the ash cloud was only part of what made the eruption remarkable. Haile Gubbi did not erupt in isolation. It sits inside the Afar Rift, one of the only places on Earth where a continent is actively breaking apart in plain view. Beneath that desert, 3 tectonic boundaries meet and pull away from one another. Africa, quite literally, is being torn open there. That reality has been known for decades. The disturbing question raised by the Haile Gubbi eruption is whether the process is moving faster than expected. Could the sudden awakening of a volcano dormant since the last ice age mean deeper changes are accelerating below East Africa? Is this eruption an isolated event, or a visible sign that one of Earth's greatest geological transformations is entering a more active phase? And if the crust beneath the Afar region is thinning more rapidly than models predicted, what could that mean for the future of the continent? These questions are no longer theoretical. The November eruption instantly drew global attention because of its scale, its location, and its implications. Satellite observations showed the ash cloud climbing into the upper atmosphere with enough force to spread across continents. Sulfur dioxide emissions measured in the first hours covered more than 20,000 square miles, or roughly 53,000 square kilometers, before the cloud continued eastward. Within days, the sulfur plume had reached the Indian subcontinent. This was Haile Gubbi's first recorded eruption in modern history. That detail matters. Volcanoes with long periods of dormancy are among the hardest to anticipate. Unlike persistently active systems that release pressure regularly, long quiet volcanoes can mask underground changes for years. Surface activity may be minimal even while magma accumulates below. By the time the pressure finds release, the eruption can be sudden and explosive. That appears to be what happened at Haile Gubbi. Located in Ethiopia's Afar region near the Erta volcanic range, Haile Gubbi is not an especially tall volcano. Rising only about 1,600 feet, or roughly 500 meters, above sea level, it lacks the imposing height often associated with major eruptions. Yet elevation does not determine eruptive power. Its importance lies underground, where it sits atop one of the thinnest and most fractured sections of continental crust on Earth. The Afar depression is often described as the birthplace of a future ocean. There, the African plate is splitting into 2 sections, the Nubian plate to the west and the Somali plate to the east. At the same time, the Arabian plate is pulling away to the northeast. These 3 tectonic boundaries meet in a triple junction beneath Ethiopia, Eritrea, and Djibouti. As the plates move apart, the crust stretches, fractures, and sinks. Magma rises upward through the thinning rock, creating volcanoes, fissures, and repeated earthquake swarms. Over immense spans of time, this kind of rifting can split a continent and create a new ocean basin. That process is exactly what scientists believe is happening in East Africa. The separation rate is slow on human timescales, often measured in millimeters or centimeters per year. In the Afar region, average plate divergence is often estimated at around 1/4 of an inch to half an inch annually, roughly 7 to 12 millimeters per year. At first glance, that seems insignificant. But rifting does not happen smoothly. Instead, decades of slow strain can be released in sudden bursts. The crust may remain relatively quiet for years, then fracture rapidly during a major intrusion of magma. During these episodes, the land can split open in days. One of the most striking examples occurred in Ethiopia in 2005, when a 60-kilometre or 37-mile dike intrusion tore through the Afar crust in just days. Massive volumes of magma forced the crust apart so quickly that what would normally take centuries happened in less than a week. Satellite observations showed the surface opening dramatically as molten rock pushed into fractures below. That event changed scientific understanding of continental breakup. Before that, many assumed rifting advanced at mostly gradual rates. The 2005 intrusion showed that tectonic extension can happen in pulses, long quiet intervals interrupted by rapid structural change. Haile Gubby's eruption may represent another such pulse. In the months before the November eruption, satellite radar detected subtle swelling in the ground near the volcano. Surface uplift measured only a few centimeters, but that movement indicated magma was accumulating beneath the volcano. Similar unrest had also been observed farther north, near Erta, one of Ethiopia's most active volcanic systems. Then Haile Gubby erupted. The timing suggests that magma movement in the broader volcanic system may have reactivated the dormant vent. Magma intruding through the rift can migrate laterally for miles underground, exploiting fractures in the crust. A pressure surge in one volcanic segment may trigger activity in another. That is one reason the eruption matters beyond the volcano itself. Haile Gubby may be evidence that the Afar rift is undergoing another phase of active magmatic extension, a period when underground magma is not merely feeding volcanoes, but physically helping pull the crust apart. Volcanism and tectonic rifting are deeply connected in Afar. As the plates diverge, pressure drops in the mantle below, allowing rock to melt. That magma rises and intrudes into fractures, pushing the crust apart even further. In effect, magma acts as both a symptom and a driver of continental separation. Each intrusion widens the rift. Each eruption marks a release of pressure. And each episode may bring the region one step closer to the eventual flooding of the depression by the sea. This is why the phrase "Africa is splitting" is not metaphorical. In geological terms, it is literal. The East African rift system extends for thousands of miles from the Afar Triangle southward through Ethiopia, Kenya, Tanzania, and Mozambique. Along this immense fracture zone, the continent is being stretched and thinned. Volcanoes dot the landscape. Earthquakes regularly shake the region. Great escarpments mark where the crust has dropped along faults. The Afar Depression is the most advanced part of this rift. Some areas there already lie below sea level. The crust is so thin that it resembles the early stages of oceanic crust formation. Lava fills widening gaps, building new rock as the continent pulls apart. Given enough time, the Red Sea could eventually flood inland through the Afar Depression, creating a new ocean that separates the Horn of Africa from the rest of the continent. That timescale is often described in millions of years. Yet the physical steps toward that future occur in bursts happening now. That is why renewed volcanic activity in Afar commands attention. It offers direct evidence of the mechanisms tearing the continent apart. The Haile Gubby eruption also underscored how much remains uncertain. Despite the Afar Rift's importance, it remains one of the least continuously monitored tectonic regions in the world. Its remote desert terrain, extreme heat, and difficult logistics limit ground observation. Many volcanic systems are monitored primarily by satellites. That means subtle warning signs may be missed, especially at volcanoes believed inactive. Haile Gubby itself had no modern eruptive record. Its apparent dormancy may have created a false sense of geological stability. Yet geological evidence suggests lava flows in the region are far younger than once believed. Even if the volcano had not erupted in recorded history, magma pathways beneath it likely remained active. The eruption demonstrated that dormant does not mean extinct. This is a crucial distinction in rift environments. Where the crust is under continuous tension, dormant volcanic systems may reactivate as tectonic stress changes. A sealed conduit can reopen. Magma can exploit old fractures. Pressure can build in hidden reservoirs. Surface silence can conceal active geological forces below. Haile Gubby's explosive awakening is a reminder that the Afar Rift is alive. Its ash plume rose high enough to disrupt aviation across a wide corridor stretching from East Africa to South Asia. Fine volcanic ash is dangerous to aircraft because it can melt inside jet engines, abrade windshields, and interfere with onboard systems. Even a remote eruption can create regional hazards when ash reaches cruising altitude. The November plume entered heavily trafficked airspace over the Red Sea and Arabian Peninsula. Flight advisories spread across multiple aviation zones as the ash drifted eastward. Sulfur dioxide emissions also remained detectable for days as the plume travelled. These atmospheric effects were dramatic, but the tectonic significance may prove more important. Large explosive eruptions in continental rift zones can reveal active magma pathways beneath the crust. The volume, height, and force of the eruption suggest significant pressurization. For a volcano with no known modern activity to generate an ash plume reaching roughly 14 kilometers indicates a robust magmatic event. That level of activity raises broader questions about the state of the rift beneath northern Ethiopia. Is magma supply increasing in the Afar region? Are dike intrusions becoming more frequent? Is crustal thinning advancing in pulses stronger than expected? These questions have become more urgent because Haile Gubby is not the only sign of unrest. Across the East African Rift, seismic activity has shown episodes of clustering in recent years. Earthquakes in rift zones often indicate fault movement or magma intrusion. When magma forces its way into the crust, it cracks surrounding rock, producing swarms of earthquakes. Such swarms can precede eruptions or major extensional events. In Afar, the relationship between earthquakes and volcanism is especially close because the crust is already stretched to a critical state. There, a relatively modest magmatic intrusion can trigger widespread faulting. Faulting, in turn, creates more pathways for magma ascent. It is a feedback loop that can rapidly reshape the crust. That is why some researchers have warned that continental breakup may not be as gradual as once imagined. The average rate of divergence remains slow, but the real structural changes occur episodically. During active pulses, years or decades of tectonic extension can happen in days or months. The crust can fracture rapidly, ground can shift, and magma can flood new openings. Recent geological observations in the Afar region show that the crust does not stretch in a steady, continuous motion. Instead, it deforms in pulses. Long periods of relative quiet are interrupted by bursts of intense activity, when magma rises from below, fractures the crust, and forces the plates farther apart over a matter of days or weeks. Those pulses are what make the region so important. They provide direct evidence that continental breakup can accelerate abruptly, even if the long-term average remains slow. This pulsing behavior has transformed how geologists interpret the Afar Rift. Rather than imagining the continent splitting apart at the same rate every year, researchers now view the process as episodic. During quiet phases, strain builds beneath the surface, while the land above shows little visible change. Then a magmatic intrusion occurs, pressure is released, and the crust moves rapidly. In those moments, the land can open by several feet, or more than a metre, almost instantly in geological terms. The volcano erupted in one of the most fragile sections of the Afar Rift, where the crust is already so thin that magma can ascend relatively easily. In some parts of the depression, the crust may be less than 12 miles thick, or about 20 kilometres. By comparison, average continental crust elsewhere is roughly 25 to 40 miles thick, around 40 to 70 kilometres. This thinning is one of the clearest indicators that the continent is transitioning toward a new geological state. As the crust becomes thinner, it also becomes weaker. Faults form more readily. Magma can exploit existing fractures. Heat from below further weaken the rock. The result is a crust increasingly prone to sudden episodes of deformation. Hailie-Gubby's eruption suggests that enough magma accumulated beneath the volcano to overcome that weakened crust and force an explosive release. The ash column that rose to approximately 45,000 feet, or nearly 14 kilometres, was evidence of significant pressure in the system. Such an eruption requires large volumes of gas-rich magma rising rapidly to the surface. That matters because magma in the Afar Rift does more than feed volcanoes. It acts as an engine of rifting. When magma intrudes into the crust, it pushes the surrounding rock apart, creating vertical sheets of molten material called dikes. These dikes can extend for dozens of miles. As they propagate, they widen the rift zone. The crust fractures to accommodate the intrusion, and the plates are forced farther apart. This process resembles what happens at mid-ocean ridges, where new ocean crust forms as tectonic plates diverge. The Afar Rift is essentially a continental version of that same mechanism. The key difference is that it is happening on land, where the crust has not yet fully transitioned into oceanic crust. That is why Afar is often described as a rare geological window into ocean formation. What makes Hailie-Gubby especially important is that it reactivated a volcanic system believed dormant for roughly 12,000 years. That suggests the underlying magmatic network in the region may be more interconnected and more active than surface records indicate. A dormant vent can remain sealed for millennia, yet still be linked to active magma movement deep below. This possibility aligns with recent observations from satellite geodesy, which has revealed widespread crustal deformation in Afar over the last several years. Small but measurable uplift and subsidence patterns indicate magma is moving beneath multiple volcanic centers, not just the ones historically considered active. These observations point to a broader system under stress. The eruption at Hailey Gubby may therefore be a symptom of regional reactivation rather than an isolated incident. If magma is intruding beneath multiple sectors of the rift, it means the crust is being stretched and pressurized over a much wider area. That increases the likelihood of additional faulting, seismic swarms, and renewed eruptions at other dormant vents. The Afar rift has seen this kind of chain reaction before. When a major dike intrusion occurred in 2005, it triggered a sequence of smaller intrusions and volcanic events over subsequent years. The crust responded not as a single isolated fracture, but as an interconnected system. Stress changes in one area altered the behavior of neighboring volcanic centers. Hailey Gubby may be another indication that such a sequence is underway. This matters far beyond Ethiopia because the Afar Rift is the northern gateway to the East African Rift System, a fracture network stretching thousands of miles southward through the continent. Changes in the Afar segment can influence the tectonic stress distribution farther along the rift. While the entire system will not suddenly rupture at once, pulses in one region may affect how strain accumulates elsewhere. That possibility has renewed concern over how continental breakup is modelled. Traditional estimates suggest the Horn of Africa may separate over a span of several million years. That overall estimate may still be broadly accurate, but if the breakup proceeds through intermittent rapid episodes, then key transitions could happen far more abruptly than the public imagines. A useful comparison is to think of a branch being bent slowly. For a long time it appears unchanged, even while stress builds inside. Then suddenly it cracks. The total bending process was gradual, but the actual break was abrupt. The Afar Rift behaves in much the same way. For centuries, even millennia, the surface may appear relatively stable. Then magma intrudes, faults slip, and the crust opens dramatically. These abrupt episodes are the moments that drive the long-term transformation. Hailey Gubby's eruption is alarming because it may indicate one of those episodes is occurring now. There are also implications for the long-term geography of East Africa. The Afar Depression already lies at or below sea level in several areas. As the crust continues thinning and subsiding, it becomes increasingly likely that marine waters from the Red Sea could eventually invade the depression. That event would not happen overnight, but each pulse of extension brings the region closer to that threshold. When that threshold is crossed, the geography of Africa would begin changing permanently. If you found this video informative, make sure to like, share, and subscribe for more in-depth coverage of the powerful natural forces shaping our world. And don't forget to tap that hype icon. Your support helps this video reach a wider audience and keeps these updates coming.